Okay, so if you're just coming in, the tests are up here. You can pick yours up if you'd like. I could tell when y'all were taking the test that there was some distress in the room. I can always get a sense for it. So what did y'all think? I mean,
it was a lot to study for.
it's a lot of material?
Yeah.
Yeah?
Just a lot of material having to cover. I know, you kind of you go to homework, but that's still a lot of material.
Yeah.
Without being able to reference formulas just going off the back of your head.
Okay, so lots of stuff, a little overwhelming. Okay. Any other comments?
Yeah, I just didn't practice enough.
Well, let's take a look at the grades. 1A, 3 Bs, 4 Cs. So we had, what, 8 people pass the test? And then 2 Ds, 8 Fs. And then you can see the distribution of the grades there on the right-hand side. Remembering that 70 is passing, but I think a lot of you are here not just to pass, but to have a decent GPA also. So I'm trying to figure out where I'd be concerned. I think this group in here, probably room for some concern. But do you remember when we started class? I mean, I kind of told you all that historically the trend is, that the we usually start with about 30 people and then end class with 15 usually. And of those 15, it just kind of depends, class to class. So hopefully this first test was some sort of indication as to, how are you going to prepare for the next one. You kind of get a feel for the way I test.
And how you grade.
And how I grade, yeah. So I try and get partial credit as long as there's something there that makes some sort of sense. If you have any questions on the way I graded something, feel free to talk to me after class. Let's see. Caleb? Jason. Jason, all right. There you go, Jason.
I look like a Caleb?
I mean, I don't know. Could be. All right. So the low is a 31. Yeah. The class average was a 61.9, 62. And then the standard deviation. Do y'all know what a standard deviation is? Standard deviation. Okay, so like if you take, let's say, the height of men, okay? I don't know what the average height is of a man on this planet, but let's just say 5'7". Okay, I don't know. I'm making this shit up right now. Okay, 5'7". You get a lot of people that would be 5'7", and then you get these people who are like 6'5", whatever, and there would be a smaller percentage that would be that tall, correct? So your average here is in the middle. A standard deviation measures how far apart your data set is. So the rule of thumb is this, that if you have a data set that's called normally distributed, then most people lie within 2 standard deviations. If you're outside of 2 standard deviations, you're considered to be an outlier, which means that's like, I don't know if David Robinson would be an outlier. He's what, 7 foot? 7'1", 7'2". So he's probably an outlier. In terms of grades, our grades, the average was a 61.9. 61.9. Let's just say 62. The standard deviation was 18 points. So what's this plus 18? 80. And then that plus 18, 98. All right. And then over here on the other end, Take away 18 from this, and what would you get? 40,
No,
44?
44.
44, and if you take 18 away from that, you'd be 26, okay? Yes? So this is saying, standard deviation-wise, everybody should lie between 26 and 98. So if you're outside of 98 and 26, you're exceptional, either exceptionally good or exceptionally poor, right? That's kind of the idea here, all right? So I would just be concerned about any group that's outside of one standard deviation. So that would be a group that would be in here. And then this group over here, I'm not saying I'm concerned. This would be a good thing for that group. So anything 80 and higher, which there's, what, 4 people in this group, and there are 4 people in this group. So that's why I would say I'm concerned about the ones on the end, because they're outside of one standard deviation, getting closer to 2. And once you get close to 2, that's like very far from the average, if that makes sense. Yeah? Okay. I don't want to harp on this test too much. You know, it's just one test. I know people are going to ask, can we do corrections and things like that? And, you know, unfortunately, my answer to you is, you know, this is college, right? You've got to show up. You've got to be ready that day. It's not about going back and fixing your mistakes. That's great. You should go fix your mistakes. That's absolutely essential that you do that. But it's coming in and being ready that day. And as you move on in college and take more courses that are more math-based, you'll find that, you know, I remember math courses that I took where you had 2 exams. 50-50. Walk in, 50% of your grade, boom, midterm. Walk in, final, 50% of your grade. You have to perform. And it's a lot of pressure. And the only way to really practice for that pressure is to, you know, figure out a good study habit. You know, like, how do you sit down? How do you prepare for a test? Do you take out, like I gave you some problems to look through? You know, did you go back in your notes? Did you go back in the book? Did you find problems like that? Did you turn off the TV, put your phone on silent, give yourself a testing environment and see how you did? I mean, these are things that you need to work on if you want to try and get yourself over here, right? So
I take it you don't do any curves, correct?
I don't think it's fair for me to do a curve on the first test. I mean, I think it would be a little, well, yeah, I want you to find motivation within yourself to do better on the next test. I don't want you to get a 70 on this and then it wind up be a, you know, I curve it to a B and then you feel like, oh, okay, well, it's a B and he's going to curve grades anyway. You know, life doesn't come with curves. Right? Yeah, so you know, that's all. I'm just trying to get everyone to be real about it. This first test, if you didn't do good, okay, you strap on, you take it, you know, approach it a different way, see how the next one goes.
I just was curious on your grading style, if you believe in that or not.
I do believe in curving, yes, but I did not curve this test yet. It's still left to me, if maybe later on, the class average on the next test is, you know, a 78. Everyone shows massive improvement. Then I can go back and say, you know what, this test was kind of an anomaly, and you know, now everyone kind of woke up and knows what's expected, and you know. But I don't want that until after we've done some more work.
I understand.
Okay.
I just, because some teachers, you know, they're frankly,
Yeah.
hard hats, and
Yeah.
it is what it is, and some are like, well,
I am open to curving, but it won't be just here's a curve for just because I need to bring the average up to a 70. Yeah, this is the same.
I'm not saying like just give it straight. I'm just saying.
Yeah. Yeah, absolutely. I'm not sitting here saying absolutely not. This is your grade. It's, you know, that's it. Suck it up. No, I'm saying yeah. Let's see how the next test goes.
And then on the extra credits for homework, you said will be later on in the class as we go along, or how does that work? Or you just leave it up to your own discretion?
Well, there's nothing in the syllabus stating that. So that what that allows me to do is later on, if I say, you know what, I'm going to let you at the end of the semester turn in all your homework for bonus, then I'll do that. But it, you know, that means you need to have been doing your homework. Yeah.
Because I know you mentioned it in your presentation.
Mm-hmm. Yeah. So just do your homework, keep it all in one place, and yes. Oh, that was if you have a time up in the top corner, I was just trying to see like when people finished, but I didn't get to mark everyone's time. Yeah. Okay, well, I think the good news, I don't know if anyone wrote this down the first day, but do you remember me going and telling you like what the averages were on the test from my past class? Does anyone still have that written down with them? No?
I think the average was a 68.
On the first test? Do you remember what the second test average was?
It went a little higher. Like
Went a little higher? Okay.
The second one was the best.
I think the second,
test being higher is mainly because of that first test being so low and that kind of wake up call.
maybe. I think it's more the material is a little easier to work with, I think. Because this is a lot of material. This first test was a lot of different things.
Review chapters, and then we had
Yeah.
3 chapters on top of that.
Yeah.
So I mean, I spent extensive amount of time studying. That's why I was just like,
Yeah.
I was
Yeah.
studying like over the weekend, and I mean, it was just.
Look, I mean, you can't beat yourself up about it. I mean, sometimes you take a test, it doesn't go as planned, you know, and even though you put in the time and the effort, you know. I think every problem that I put on that test, I mean, this is my opinion because I made the test, but I mean, I think every problem was fair in the sense that it wasn't something you'd never seen, you know, it was from something we had done.
I thought the average rate of change was, well, we just covered that thing like the class before.
Average rate of change?
I think it was.
I could understand you being a little upset about me putting 2 parabolas to graph because that was the last thing we did. You know, numbers 10 and 11. But average rate of change, we had covered that several weeks ago, probably 2 weeks ago.
11 wasn't bad though because that was I can't think of the name of the notation.
Standard form.
Yeah, that
That
was
one,
standard form.
that one I specifically studied for, so I knew I was gonna argue it. Like, I like it.
For me, it was like x plus h, then f minus f of x, all that.
Well, you know what I did, like, right before the test, like, I was like, literally like memorizing the formulas, and then as soon as like, he said, go, I like literally wrote them down.
All right, well, look,
'Cause I forgot about
the train still needs to leave the station here, so we got to keep going.
I digress.
All right, and we're going to move into chapter 5.
We're not gonna go with 4.5?
The inequality ones.
Did you say we're gonna leave it for later?
Yeah, we can do it. We can do it now. We can do it later. It's kind of up to y'all. Do y'all feel like having fresh new material, or do you want to go into? No, you don't want fresh new.
No, I do.
Oh, you do want fresh new. Let's start with some fresh new, okay? That way it'll feel like a clean slate.
Are we going to?
We will go back to it. We will go back to it. Yes. Yes. You'll have it'll be built into it. Yeah. The main thing is we haven't looked at quadratic inequalities and rational inequalities, so we'll fit it in. But yeah, let's kind of clear the slate here and start with the fresh concept. I think that'll be good.
I know you weren't in your office today, but you're gonna be on.
Yeah, did I send out an email about that?
No, you did
No, I didn't. I had an appointment that I had to make at 10. I had to cancel my other class too, so I apologize about that.
But Tuesday.
I'll be there. Everything back to normal now. Yeah. Okay, so 5.1, we are looking at polynomial functions, and here's basically where we're at right now. When it comes to graphing functions, in this class, I alluded to this, I don't know if it was last class or the class before, that there are 6 types of functions that we need to be able to graph as college algebra students. We should be comfortable with. The first one, linear functions. All right, y equals mx plus b. Everyone should be able to draw a nice, real detailed graph of a line. Quadratic. Quadratic. Okay.
Then it was cubic, sorry.
Hold on. These are the parabolas, right? Now, don't confuse what I'm doing here with our toolbox functions. Our toolbox functions were this set of functions that we knew what basically they look like, and then we can move them up, down, left, right? And we could stretch them and reflect them, but we really didn't get a real good picture. I mean, we got a sketch, but we didn't get like all the real nice x-intercepts and y-intercepts. You understand what I'm saying? When we say graph a function, we mean that there's a little more detail in the function or in the graph than there is with just a quick sketch. So we should all be able to do a really nice graph of a line, and now we should be able to do parabolas, which is what you were tested on for numbers 10 and number 11. If the parabola is given to you in standard form or in expanded form, you should be able to graph it. Up, down, right? Does it open up or down? Is it, where's the vertex? Does it have x-intercepts? What's the y-intercept? That sort of thing, yes? Okay, now here are the rest. Polynomial functions, which is what this is about today. And then after that, we're going to do rational functions. Then we're going to do exponential. And last, we're going to do logarithmic. Those are the 6 types of functions that we should be able to graph. These 2, we've got, right? So let's talk about this set of functions called polynomial functions. A polynomial function is the sum or difference of terms, each of which is a number times x raised to a non-negative integer power. What? What are you talking about? So here are some examples. So the first one I have there, f of x equals 3x plus 5. Okay? Is this the sum or difference of terms, each of which has an x, a number in front of x, and the x is raised to a non-negative integer? So what are integers? That's what it said up here, right? Non-negative integer, power. So what are integers? Do y'all know what integers are? 1, 2, 3.
It's whole numbers,
Yeah.
positive or negative.
And it could be negative also. So these are integers, right? It goes forever in both directions.
But in this particular case, we're talking about only positive ones?
We are talking about non-negative, right? Which means not these, right? We're talking about this group right here. Understand? So a polynomial function is a function where you have terms. Terms are separated by addition and subtraction. Each of these has a number in front of a power of x, where the power has to come from this list. So does everyone agree that 3 times x satisfies that?
Yeah.
This is x to what power?
To the
First power. Okay, this is a number in front of x. Whoa, is there an x?
No.
Is there an x? Now there's an x, right? Isn't x to the 0 1?
That's kind of like that.
It's kind of like a hidden 1, okay? So all we need to realize is that there is actually a power of x on this. It's just x to the 0. So this does qualify as a polynomial function. But you probably recognize it more as a what? As a linear function. So what I'm telling you is that that is also a polynomial function. All right? Let's look at the next one. F of x equals x squared minus 4x. So do we have the sum or difference of terms, each of which has a number in front of x to a power? Yes. There's a 1 in front of x squared. That power is a positive integer. I have negative 4 in front of x to the first power. 1 is a positive integer. And I actually do have plus a 0 out here, right? I mean,
Plus
0, x to the 0. But we don't need to worry about it, okay?
Because we assume it's there.
Yeah. So this satisfy it, right? But what do we recognize this as being? Quadratic, a parabola, right? But now what we have on top of that is something like this one, negative x cubed plus 9x. That is also a polynomial function because we have terms, right? 2 terms, number negative 1 in front of x to a positive integer plus a number in front of x to a 1, which is a positive integer. So this is also a polynomial. Is it okay that I don't have an x squared in there? Sure. Actually, you could, if you want, say that it does have an x squared? Would you agree that that is the same thing? So it does have an x squared. We just don't write it because it's really a 0. So that is also a polynomial function. And any combination that we can make of terms with x to positive integer powers is going to qualify as being a polynomial. So the last one up there, x to the 5th minus 4x cubed plus x squared minus 4x to the 6th.
So basically, as long as the exponent is 0 or positive, it's
Positive integer, yes. Yep. And where you have sum and difference between them. Okay? So every line is a polynomial, isn't it? Every parabola is a polynomial. So if you want to look at it like, how can I do it? This might make sense. I'm going to draw Texas for you. Oh, whoa. Okay. Wow. That's Texas.
well, you got the hammer.
Welcome to Texas. Right?
The arrowheads.
This is
This is not drawing class.
linear functions is like Texas. Lives within a bigger set of things, right? Which is, this is the United States, please, again. Don't worry about it. Right? So the entire United States are polynomials.
Florida's bigger than I remembered.
Things have changed. You haven't been keeping track of the Weather Channel lately? Okay.
Global warming.
Blame
Obama.
So linear functions belong to polynomials, right? Polynomials are the entire United States, right? But you have other classifications. California. What? Quadratics live in here? Right? Quadratics. But see, linear functions are not quadratics. Quadratics are not linear, right? So polynomials are a larger group of functions, and we need to be able to graph those. We can handle two types right now. But what about the types of polynomials that aren't like these two? Like where you have an x cubed in there. Or like the last one there where, what's the highest power of x you see in that last one? 6. So what's that going to look like, right? How do we graph them? So here's a couple of things we need to first get squared away, some language. When you're looking at a polynomial function, there's something called the degree of the polynomial, which is just the highest power of x that appears in the polynomial. So quickly, let's look at these. What is the degree of this polynomial right here? What's the degree? 1. Highest power of x. Right? What's the power on this x right here? 1. So that's the highest power. The degree of that polynomial is 1. The degree of this polynomial? 2. This one? 3. This one? 6. So be careful. It doesn't have to be in order, right? It's not the first one that appears. It's the highest one that appears. So 6th. So this would be a 6th degree polynomial, a 3 or degree 3 polynomial. This would be a 2 degree 1. Okay, and then you have another term here, another definition, the leading coefficient. The leading coefficient is the number that is in front of the highest power of x. The number, not the x, but the number. So looking back up here, what is the leading coefficient of that first function that I've highlighted there? 3. It's the number in front of the highest power of x. How about with this one? What's the degree, or sorry, not degree, the leading coefficient of that one? 1. It's the number in front of x squared, which is a 1. What is the leading coefficient of this one? -1. And the leading coefficient of this one? -4. Okay? So that's what your next test is going to be. I'm just going to give you 100 polynomials, and you just have to find the degree and leading coefficient.
Hey, that's a
Right?
good test.
That sound like a good test?
Do it right now.
Let's do it right now.
Just do it right now for a
Okay, so we just did that. All right, so this is just reminding you that a line is a degree 1 polynomial, right? All lines should be degree 1 polynomials. All parabolas should be degree 2 polynomials. And then we have a general formula for an n degree polynomial. I want to write this out on the board, but well, you know what? I'll just walk over to that board instead so I don't have to write this out. Is everyone familiar on that first one, the degree 1 polynomial? Everyone recognize the form of y equals mx plus b? Excuse me. Remember that? This is a line. The m is a number, right? But it represented the slope of the line, didn't it? So it had special meaning in a line. And the b is also just a number, and that was the y-intercept, yeah? Yes? Okay. And then whenever we had parabolas and we expanded them out, we had an a, a b, and a c, and those were just the three numbers, right? These three numbers, and they helped us also. They helped us find the vertex, right? Sometimes we use them for a quadratic formula if we have to find the x-intercepts, all right? But if we get like a degree 3 polynomial, or degree 4, degree 5, or anything higher, then we like to write it like this. And then you look at it and you go, what the hell? So like, look at this. What if I wrote a degree 3 polynomial like this? ax cubed plus bx squared plus cx plus d. I could have come in today and said, hey everyone, this is what a third degree polynomial looks like. We have a, b, c, and d now, right? These are just three numbers. I could have done that, but this is what I'm giving you instead. Or I could have said fourth degree. Just hang tight if you don't know what the hell I'm talking about. Just hang tight for a second. This will hopefully come together. Cx squared plus dx plus e. And I say, all right, everyone, this is what a fourth degree polynomial looks like. And we have a, b, c, d, and e now, right? So why not do this? Why do that instead? Why have this crazy looking notation instead of just saying a, b, c, d? Anyone know why this isn't going to work? To just keep on defining it like this? Like the fifth degree, sixth degree, seventh? You're going to run out of letters, right? It's going to get too long.
You can start drawing animals.
Yeah, you could. You could.
It wouldn't be very efficient.
We do something else, though. What we do is, instead of using A, B, C,
You solve for elephant.
what we do is we call the number in front of the highest power of x. Okay, x to the n is the highest power. We call the number in front of it, instead of a, we call it a sub n. And then the one next to it would be the next power down, would be a sub n minus 1. So let me give you an example over here. Instead of doing this, right? Instead of doing this, what I would do is this. What's the highest power here? 4. So I would go a sub 4, x to the 4th, plus a sub 3, x to the 3, plus a sub 2, x to the 2, plus a sub 1, x to the 1, plus a sub, what's the power on the x here? 0, a sub 0.
Are you saying a sub 0?
A sub, like subscript. So a sub 4, a subscript 4, x to the 4th. And see, if I do it this way, and I'm telling you that's just a number, that's just a number, that's just a number, that's just a number, then if I wanted to go and try and illustrate what a degree 300 polynomial looked like, it would be y equals a sub 300, x to the 300, right? Plus a sub 299, x to the 299, plus all the way until I get down to yada yada.
Is that a 1 or is that a...
Where?
Where it says right there.
That's a 1.
That's a 1.
Yep.
So the A's would be the leading coefficients and the N's would be the powers?
Okay, the A's would be coefficients. The one right here is the leading coefficient, just this one. Because remember, the leading coefficient is the one that's attached to the highest power of x. All the other ones are just called coefficients, the numbers in front of your variables. Does that make sense?
So over
Yes.
there on the second line and the third line are typically the same thing
Where?
that you wrote down.
Over here?
Yeah.
Yeah, these are exactly the same, except this person is calling these numbers A, B, C, D, and E, and I'm calling them a sub 4, a sub 3, a sub 2, a sub 1, a sub 0. My method is going to be better than this person's method if the polynomial gets to degree higher than 26, because they'll run out of letters. I won't.
You see that a lot.
Do you see that? And this is what we do in mathematics all the time. When we try and generalize something, nothing says that the degree of a polynomial has to be less than the number of letters you have. I mean, there's no restriction. So this is a more mathematical way of writing it. It avoids any danger of running out of letters. That's all it is. But when we look at it, we're like, well, why do they do that? They just want to make math look hard. But that's all it is. It's a way to get around that. Understand?
It's because they want to make math look easier.
I guess you could say that also.
Well, the thing is like, I actually see this in like economics class.
Uh-huh.
I'm thinking macro.
Yeah.
And we use that, and now that makes sense why he uses that, because it keeps everything, when you're just talking more just math terms, it makes sense because you're keeping everything together.
Especially in economics. One of the most famous problems in economics was where a computer was used to solve the problem. There were 40 unknown variables in the problem, and it was a problem that had been around for a long time, and they used a computer to solve it. And there you couldn't call each of the variables A, B, C, D, E. You have 40 of them, like you're going to run out of letters. So I guess you could say, you know, A, B, C, D, all the way till you get to Z, and then you could have said like AA, BB, or something. I don't know. You could get weird like that, but even then you're going to run out, or it's going to look weird.
Right.
This never has an issue. So, okay, so all these things in front, a sub n minus 1, we just said those are just numbers. There's one condition, a sub n can't be 0. The reason why a sub n can't be 0 is because if this number right here is 0, then the x to the n isn't there, is it? Right? And then n is not the highest power of x anymore. So whatever the number is, if you're going to say you have a degree n polynomial, then you must have a number in front of x to the n. There has to be a number other than 0. I hopefully explained why it was so ugly looking. Did I kind of explain? Okay. Now let's talk about some properties of polynomials, like what they look like. So I have them up there so you can kind of visualize them. This right here is the graph of this polynomial function right here. I don't know if y'all, can y'all see that okay? X to the 6th plus x to the 5th minus 14x to the 4th minus 24x cubed. If you graph it, that's what it looks like. And we are going to need to be able to do that.
That kind of looks funky.
Does?
Looks like Florida.
Looks like Florida. Let me see if I can move this.
It's got to be all those old people.
I'm going to change my zooming here. There we go. That's a good one. So take a look at this. I think I might scale it just a little bit too. Oh, maybe not. That's good. So what it appears to do, what it appears to do, you can't really tell, but these are like arrows, okay? They keep going up to get forever, kind of like the parabola did, right? Both sides. So this side goes up forever, and as you move to the left, it just keeps going up and up and up. Yes? As I move to the right, it keeps going up and up and up and up. It's just very, very steep. But this one comes down, crosses through the x-axis, right? Comes down, has a local minimum, comes back up through the x-axis, has a local maximum, comes back down, touches the x-axis, and then goes back down. You can't see it here, but it goes down, curves back up.